So this is where we left last time yesterday on the SAP Oracle, and thanks to Rod for the shout out and for the reaction to the video. I think that was really cool. And thanks to this, I also realized and found out it was open just here. So the repository here, it's interesting. This seems to be part of the, was it like the IBM's quantum challenge thing, or sort of a contest like where you had to solve different problems on a weekly basis, something like this? I don't know. Maybe I'm wrong. Um, but there's definitely stuff here to try and reproduce. But let's try and focus on the paper first and see how we get there and all that stuff. So I think I gotta download that again actually. Uh, what I was targeting for today's session was the go forward with the Oracle. If that will load. Perfect. Cool. So we went through that, and as I said, I'll go back to some of those parts and some of the things that I didn't understand yesterday. But we've gone through these. And now, what should I do now? Complete circuit, the Oracle circuit design. So I think that's where I should now. Complete circuit implementation. I think that's where. Oh, wait a second. Oh, no. Okay. The Oracle operator. Okay. So these O's, these gates are they basically the SAP oracles or what? Because we discussed and apply with. Give me a second. So solve Maxwell problem. Set the threshold value. Yeah, this we read yesterday. This we went through yesterday. Increasing T. How to apply the above procedure when with a given star graph. First, we prepare 5 data qubits to describe the state of the nodes. When there is an edge between A and B as a cat checker for each edge, we introduce the following SAP oracle. Yeah, that's what we did yesterday. After execution of OS for all edges, we set the threshold value T and perform the phase inversion. Oh, okay, so this is where I'll start today. So let me close that up, and so here S is an accumulator register, large enough to store the number of cat edges. For this problem, there's going to be 3 qubits for the register are enough. So we can definitely so close that. So I'm considering whether to use that or whether because basically that's what they're saying is that, okay, so we need 3 qubits for that register. That should be enough for the accumulator register. Good. So after the execution of OS for all edges, we what was I? When the states of A and B are different, the edge between A and B is cat, and the information of cat edges on S is updated. We can implement OS using a quantum increment circuit as showed in figure 5b, and that is 5b. That's what we did yesterday. Okay. After the execution of OS for O sub S for all edges, we set the threshold value T and perform the phase inversion operation for inputs that equal or exceed T. The flag qubit. Okay, so T was basically the trick here to say set something T that it's of course lower or equal to the max amount of edges, and then you're kind of trying to find those solutions using Grover, in terms of the stuff that exceeds t. And if the output is legal, you increase t. So if you actually find something, then you try to find something bigger, right? Because Grover kind of limits you to find, you know, a set of particular elements. You can't. Let's put it this way: you can't easily. I think you can't easily tweak Grover to just, you know, built in basically search for stuff, you know, bigger than something and stuff like that. So it's you're searching for specifically flagged items in your input, and so if t returns to a value taken into a prior iteration, because you the cruise output is illegal, exactly. So if it turns to a value taken in a prior iteration, then it means that you found the max cat. So okay, so you're basically flagging everything that you're basically flagging. So after the execution of OS for all edges, we set the threshold value t and perform the phase inversion operation for inputs that equal or exceed t using the flag qubit. So we're gonna need threshold value t and perform the phase inversion. But how are you gonna? Okay, so you're gonna need to have some kind of counter, something to count. In this problem, t corresponding to max cat is obviously 4. We show the circuit correspond to this operation in figure 6. So this is figure 6. So your Oracle operator. So this is definitely O sub S, I think, and this is just to uncompute. And here you're basically phase shifting using using a flag, so using an ancilla qubit. It's a sequence of all sub oracles OS. After the execution of P shift, we have to uncompute, to propagate sign reversal for inputs equal to or exceeding the threshold value. T, to propagate sign reversal for inputs equal. Not entirely sure what that means. But then you're gonna have, so O is like the combination of all the O sub S, and phase shift is gonna have to, I'm just trying to, before I go ahead and read, I'm gonna start to find how would I do that. So I would so you would flag this for all so you would flag, you need to count the oh well, I'm stupid. I mean, it is obviously in the accumulator, right? I mean, you're gonna basically have that actually encoded in the first 3 qubits, aren't you? Yeah, so here you've got, okay, yeah. That's interesting. Here you've got 1 cat. So if I wanna do a test here. If so let's say the first 3 are our data qubits. So if I say, for example, that I'm checking this edge and I'm checking also this edge, right? Just as an idea, and then I do the same here. So now I'm gonna have basically, and remember this is So how can I paint here? So these is the separation of my registers, right? So here we've got data, and this is the accumulator. So okay, but the beauty of this is that in each of the elements of your resulting superposition, you're having and the if you take a look here, if you can, if you take a look at the, because this is just like a hover element. So, but if you take a look at basically the amplitude, the element, right? So this is the number like 0, 1, 0, 0, 1, 0. So the 3 qubits on the left side tell you how many cats you've got on the configuration expressed by the 3 qubits on the right side. So 0, 1, 0 has 2 cats, so that's why you've got like a 0, 1, 0 in the yeah, in the first three 3 qubits. Okay, so then the phase shifting is only going to be as a function of the accumulator value. Yeah, but that's a cool thing about working with the superposition in this case. Cool. So you probably do something like you'd phase shift. For example, just say I want to phase shift everything that's 2 or bigger. So I would go ahead and use some of those less than. Toggles the qubit. No, but I don't want to I don't want to toggle it. I want to phase. Gradient. I would use something like that though. See what they say. So complete circuit representation. When t equals 4, we can get this and this as a solution by combining the above oracle and diffusion and repeating those the appropriate number of times. When implementing a processor with the current QV, the proposed circuit is too large in both number of qubits and depth. For example, the half adder contains a Toffoli gate that requires 6 control X gates on IBM Q devices. From the discussion in section 2, the upper limit of CX gates that can be used to obtain valid results is understood to be around 10, taking into account the need to uncompute portions of the circuit. We will not be able to include multiple suboracles and anticipate a successful execution. Okay, so basically that's what it's saying is this is not doable with current processors because of the amount of gates that you require to just have the half adder, so the actual part that increments. We have already proposed a method to reduce CX gates by eliminating adders and increasing ancilla qubits. We still need 36 CX gates per iteration to solve MaxCAD in a smaller graph. Needless to say, there is room for improvement in our proposed oracles. However, in order to solve MaxCAD with Grover's algorithm on a real processor, in the near future, drastic improvements are necessary. Okay. Therefore, we need to propose a new data structure that does not store the number of cut edges in binary data. Okay, so now we're getting into the... okay, but I still wanted to... Let's try to implement the ideal case. Okay. Let's try to implement the ideal case. Maybe that's sort of as a goal for this video, and then let's try to, and then we'll go and do the approximated Grover search for MaxCAD, and that's I think the sort of optimized version for current processors. Okay, so I'll try to see if I can maybe use the RIDE. Can I use the RIDE? I want to use the same size. I don't know if they use what they're using 3 qubits. Yeah, one for each. Okay, so I'm gonna stick to that 3 qubits. That's what I have here. And and for the T they said, right, I don't know where I read that, but they said 3 qubits is enough, yeah. Um, but here, I don't know why this, like, 5 qubits though. 3 qubits is enough. I need 3 qubits for the solution. And 3 qubits for the accumulator register. Okay. Uh, so how would I implement that phase shift? So I would say complete circuit implementation. Okay, no, this. So I would basically need to shift the phases of those elements that say have a number bigger than 2, right? Or bigger or equal than 2. I mean, in that particular case, I could just trick that by saying if that, I mean, I could just implement that by saying if that qubit is 1, I know that the number must be 2 or bigger, right? So, no, okay, not. But then if it's 0, but then this must be 1. Okay, so and and then the accumulator. So they're using a flag. So I'm gonna use a. This is gonna be. See, sometimes I have to drag the gate just to make sure that I have the wire. So that's gonna be our flag. And so what if I just do something like this? What am I doing? This is in a minus state. And so so this is, wait a second, this should be easy. This should be trivial. I mean, actually, what I could say is, the easiest but probably not efficient way to do that is toggles if input A is greater than input B. Greater than. So I would say here I'll need to set the input to it's input A and B. So I'm gonna say, how do I do that here? How do I do that here? Where's A? I lost the, oh yeah, here. Input A. So I'm gonna say this is the input, and then I'm gonna say that input B is 2, right? So it basically toggles this qubit for the cases, the last one, for the cases where this is 2 or bigger. So if I take a look at that subsystem concretely, let's see. Oh, I can't take a look at the amplitudes here. That sucks. So I have got to take a look at these here. So there's a 1 in here because we've got 2, and there's a 1 here because we've got 2. And here we've got like 0 because there's 1, 0 because there's 1, 0 because there's 1, 0 because there's 1, and 0 because there's 0, and 0 equals 0. So those two elements now are toggled, and now based on this toggle, um, I could basically flip the faces of those two elements, right? So if I now do this, that effectively does the job, right? Because it just flips the faces of these two elements, and then I basically should toggle that off to go back to should toggle. I don't know what I'm talking about. So now I should basically uncompute that. So I should say for input A here, toggle. Okay, so I kind of I brought them back. So this is just, and this is, you know, I'm not looking for the most efficient way of implementing this right now. I'm just trying to kind of figure out how I would do this in an ideal case, and it's definitely not the most efficient way to do that. It's just Quirk allows me to do these things, like, you know, dynamically defining these, and then and I think that's pretty helpful. If you'd have to implement that in code, like, you would do this differently. So the combination of b equals 2 and the input A, it's something you would basically do here. So you would basically encode something here that toggles that if it's bigger than 2, right? So you could probably do that with a series of control nodes. Then flip and then uncompute. That's one way to do it. I'm sure they do this in a way better way, but we can take a look at this. I don't know. There's no reference here whether the code is, but maybe the code is there where where Rod pointed out. Maybe it's there. So if I take a look at the notifications, maybe the code is here for the p shift operation or block. Might be here. P shift. So if I so that's counting the cat edges. Creating an oracle. Okay, that's probably it. No, I don't know. And then uncomputing. Yeah, it seems like that's it, because I think that this qubit is probably what they call the flag, and so here you've got the phase shifting with Toffoli gates, right? So okay, yeah, that's a way better way to do that. Essentially, that's a control Z. Yeah, essentially that's a control Z. Okay, because here the example they're using is if. Okay, so oh yeah, I'm so stupid. Oh my god, I'm so stupid. Yeah. So you can you can basically say this is how you overcomplicate stuff. So you can basically say if you wanna say bigger than 2, I mean it's just 3. Like if there's a 1 here, it's definitely bigger than 2, right? Okay, if we say bigger or equal than 2, then probably gonna have a different combination. But basically, you can also do it this way. So you're here, and then you're gonna say basically can turn that into a 1, and then use a control Z and say no, that doesn't work. What am I seeing wrong here? So there is adding in here. So cutting edges. So so here this is the accumulator, right? And so you're adding, and then you're doing Control Z based on these. Control Z. And then you're uncomputing. So you gotta uncompute maybe for this to work out, for the phases to be there. I don't get it. That's what they. Is that what they're saying here? As the execution of P shift, we have to uncompute to propagate sign reversal for inputs equal to or exceeding the threshold value t. Why do you have to uncompute for this to work? Don't quite get it. So if I now do -1 if I uncompute, so I'm doing this, and now I do this, and I do -1, and I'm closing that up. But that's not what I want. So here we've got, okay, so we've never got an example where, okay, that's why. That's why. So in my example, that if you do it this way, yeah, that works, okay. Because in my example, I either have 1 or 2 cats, right? It's just because of the example that I've put in here. But in their case, you're getting, you can see that all 8 output states have similar probabilities of being measured and initialized to 0. It's not being measured. Phase slip is something you won't be able to see in the probability distribution. Oh, wait a second. Please note the result count probability distribution. You can see that all 8 output states have similar probabilities of being measured, and that Q3, Q6 are initialized to 0. The Q7th, which is not being measured, is always the minus state. Thus, the phase flip is something you won't be able to see in the probability distribution. Yeah, sure. I mean, you see exactly. So here, but if I take a look at this here, I don't really have to compute to see the phase flips. I see them here. But you wanna, I mean, is uncomputing really necessary? That's a question, right? I mean, I don't know. Maybe to free, I don't know if it's necessary in computing. I mean, here you can see those already. So you really shouldn't care whether the accumulator is reset to 0, because what you're doing with uncomputing, you're basically resetting the accumulator registry, right? Yeah, you're just resetting the accumulator registry. So you see here, this element and this element have flipped phases, and that's what we want. Those are the ones that they have 2 cats, basically. 2 cats, 2 cats. Yeah. I don't know whether you need to uncompute. That's still not clear to me. Because I wonder whether Grover will work anyway in this setup. So let me do something now. I'll basically compact all that into I'll pack that into actual boxes like they did here, so I can build the rest of Grover's algorithm on top of that. And you know, see if it works at all. So if now I say make gate, so make gate, and I will say I want from 1 until, is it like 1, 2, 3, 4, 5, 6? So the 6, yeah. And so this is going to be the, I would say, OS. Correct? OS. Yeah. So now I can basically, and now I can say make gate, and I'll do 6, 7, no, 7, 8, and this is going to be, or 8, 8, 8, 8, and this is going to be the, this is going to be P shift, P shift, and now I'm going to do make gate 9, 10, till like, this is 1, 2, 3, 4, 5, 6. Yeah, so that's going to be basically underscore OS. So for me, that's going to be basically the OS dagger, so to say, to uncompute. Okay. And again, it's not OS. Sorry, that's the wrong naming. This is just O. It's not OS because OS would be one of those blocks. So this would be the full O, so to say. But can I? I think if I can I tweak that in the URL? Yeah. So I'll call that O, and I'll call that underscore O, and I reload the page. That's it. That works. Cool. So now, if I now go, I'll do that on a separate quirk so I don't lose that, just in case it's not working. And now I will basically do the same. So I'll do, this is going to be my starting point here. So these, and then we're going to have like, basically the, I'm stupid. I should actually, if I want to have my custom gates, I should do this, and I should clear the circuit, and then, exactly, and then do O. No, P shift, why is it? That's not what I wanted. That's not what I wanted. So I don't want that P shift in here the way this looks like. So I just I just want P shift to be 3 qubits. So okay, but P shift we can. I think that was just because of the way I created the. But this I can simply do like that. Like that. And so another question is that, is this enough, or should I do that? If I do that, then I go back here. Okay, so okay, good. Maybe the reason. Maybe the reason for uncomputing is that you can, for you to be able to see those phases in here. Is this true? Because here, if I don't uncompute, then I can't see them. Cool. Because then there's just nasty entanglement. So now, okay, so now I know why. Cool. So the uncomputing is needed so you can kind of focus on that subsystem, at least see those things. Because otherwise you're entangling. The oracle is, these oracle parts are entangling this whole things and that thing, and then you can't really calculate the proper phases. So another question is, okay, so now how do we implement the rest of Grover's algorithm just on these 3 qubits, really? Because now you're kind of done, so you have the elements that you want to look for. So then, now the way you would go about it is uh, the mean, the inverse about the mean, and you need that. If you don't uncompute, you're not going to be able to apply Grover's algorithm just on these 3 qubits because you're not going to have that phase information available. I think that's not going to work out. Then, um, and so now I think you would go about. I think that was in this particular setup. You need to do something like this. If I remember well, I think. Grover's diffusion operator. Yeah, exactly. So now still, okay, so it's a control Z actually. Second, it's a control Z, and then I can do basically X gates in here, X gates in here, X gates, and then Hономarts. Hономarts basically, and here we go. So that's the diffusion operator, which I basically could also pack into a custom gate. So I'll make that gate, and I'll say this is 1, 2, 3, 5. Okay, and I'll just say here it's from 1 till 3. That's all I want, and that's gonna call it G or diffusion, diffu. Okay. So that already gives me that, because it's with 3 qubits you just need 1 iteration. Honestly, that already gives me the amplitude, the elements that I want. So now I'm curious, if I don't uncompute, does this work at all? Interesting. That doesn't work because of the entanglement. I mean, it kind of almost works in the sense that no, it doesn't work at all. It doesn't work at all. So this is interesting. So I mean, if we don't uncompute, then we don't get those uh, phases back somehow. So I think that's pretty much it, really. I mean, that's the ideal solution. Works, as you can see, finds those 2 cats, and basically cat edges 2. Yeah, I mean, I think that's it, right? I'm not missing any of the any kind of the details in here. I mean, that's the ideal solution. So it's the problem is definitely how do you implement that on an existing, you know, on an existing QPU. But it's a bit confusing me that we're now here talking about like t equals 4. That's not the same problem, is it? It's a bit confusing. Because you just need 3 qubits, and cat edges equals 2 is the max cat, right? Hmm. I mean, again, I don't know whether I've 0 and 2. I think actually it was probably just coincidence, but I think here I've implemented that. This is no 0, no 1, no 2. I basically implemented exactly that example, right? 0, 1, 2. And so the combination of like white, black, and white, so 0, 1, 0, or 1, 0, 1, right? They're both the solutions that I find. Here 0, 1, 0 or 1, 0, 1. So those are the 2 solutions that I find here. I mean, to be correct, that's okay. That's the easier way to say it. 0, 0, 1, 0, 1. So those are the 2 solutions that you want to find. Okay, yeah. I think that's it, honestly. Now the next step in the next video would be to basically go through the approximated Grover search for MaxCat. So how do we take that and really break it down in a way that we can implement it in an actual QPU. That will be really interesting. Here they talk about this, the limitations of the amount of CX gates and all this kind of stuff. And again, I will go through all those things in detail at the very end. I just first want to go through the whole, through sort of the actual algorithm, and then kind of reasoning about, you know, why is it implemented this way? What are the limitations of the IBM Q devices in this case, and all this kind of stuff. Good. And so the approximated group research will be the next thing. Implementation of the Oracle virtual vertex again. So this is where it gets interesting. Implementation of diffusion, that's definitely also interesting. And and then basically there is some actual figures in here that I don't know what they're about, and then that's it really. So I'll do that, and then we'll probably try to reproduce the code, the actual code that they have. I don't know if in the appendices or in the repository that that Rod shared. But yeah, that's really interesting. Take a look. I'm also interested in taking a look at how they evaluate the efficiency. This just because I don't know this stuff. So how do they evaluate performance? I mean, that's just interesting. So I'm gonna dive into these and quantum volume as well at the end. So this is not gonna be just the algorithm. But it's going to be the algorithm, it's going to be the reproduction of the actual code, and it's going to be to dive into the way we analyze, or the way they analyze these type of circuits, and how do you do that? Pretty cool. That's a really cool paper. I'm going to spend some time in here the next days, definitely.